My today's topic is about continuous probability distribution, and I'm going to talk about continuous random variable. And and when we talk about continuous random variable, then its corresponding probability function is known as PDF, probability density function. Probability density function has similar properties just like its counterparts. Probability mass functions have certain properties, you already know that. Probability mass function is always non-negative. Probability mass functions sum total is always 1. Just like that, probability density function is always non-negative. So therefore I have written here fx is greater than or equal to 0. And the sum total, since I'm discussing about, I'm actually talking about or interested about a continuous case, the summation will be replaced by integration, and I can take the integration from minus infinity to plus infinity. That means I am taking the summation over all possible values on the real line, and that sum total is 1. You already know that. And when we talk about a random variable having certain values within the range small a and small b included, then that probability is calculated by integrating the function fx from a to b. And integration of a certain function from lower limit to certain upper limit is nothing but the area under the curve fx bounded by the axis and the ordinates and the curve itself. You already know that. So when we talk about finding probabilities in case of continuous case, actually we are interested about we are talking about finding the areas under the curve. Okay, so this is all about probability density function. The first two properties are already known to you because you have encountered these properties in our previous note of discrete case. Now here is a problem for you. The problem says that the probability density function of the random variable capital X is given by fx equal to c by root x when x lies between 0 and 4, and it's 0 when elsewhere. What do we mean by elsewhere? Elsewhere means actually literally elsewhere means that x is either less than 0 or x is greater than 4. That is meant by x elsewhere. Now in the structure of the problem is such that if we take the values of x lesser than 0, that means here we are considering the negative numbers, negative real numbers, then the function will be undefined because there is a square root sign. Under square root there shall not be any negative number because probabilities are always based upon real numbers, real lines. Complex number system will not come over here. And therefore if we talk about x less than 0, the function becomes undefined. So here elsewhere, according to this problem, elsewhere means x is greater than 4. So when x is greater than 4, the probability value is 0. So that is how my probability function is defined. Okay, now we are going to find the value of this constant c and the probabilities which is written over here. One probability is probability that the random variable takes values less than 1 by 4, and probability that the random variable takes values greater than 1. Remember, I am talking about continuous case, not the discrete case right now. First of all, I shall check whether this probability function is indeed a probability density function or not. How to check it? Since the above function is defined in this range from 0 to 4, I can take the sum. We know that the sum total of this probability function is always 1 if we integrate over the entire real line. So from minus infinity to plus infinity, fx dx is equal to 1 from the property of PDF. Now I am breaking this range into 3 halves. One is from minus infinity to 0, another is from 0 to 4, and another is from 4 to plus infinity. Now you see, when fx is the value of x, the values of x are between minus infinity and 0, the function is actually undefined. So we have put 0 over here. When x takes values greater than 4, okay, then also the functional value is 0. Here I have substituted 2 zeros, but remember one thing, that 0 has been substituted because the value of the probability is 0, and that 0 is substituted because the function is undefined. So there are two meanings for two two reasons for doing that. Okay, so the function is only defined when x lies between 0 and 4, and therefore I have put the functional value over here, which is c by root x. Now you integrate. If we integrate this, we get 2 root x, and c is constant, it comes outside the integration sign. Put the limits. If you put the limits, you will get two possible values for c. One is plus 1 by 4, another is minus 1 by 4. We shall not consider minus 1 by 4, because you see, if we put minus 1 by 4 over here, then the function fx becomes negative. And since fx is a probability function, it cannot be negative. So the only possibility for c is 1 by 4. Therefore, I have mentioned c equals to 1 by 4 since fx is a PDF. Okay, so by using this property, that minus infinity to plus infinity fx ds total probability or total area is 1, using this property I have found out the value of c, the constant c, and therefore my probability density function now takes the following form. It becomes, sorry, this should be, here is a mistake. Okay, you just avoid, just ignore it. I shall rectify it later on before uploading the note. It should be density, not mass. Remember, it's a grave mistake. So it's a printing mistake over here. So the probability density function now becomes fx equal to 1 by 4 root x. I have substituted the value of c over here. It becomes 1 by 4 root x when x lies between 0 and 4, and 0 elsewhere. Now our job is to find the probability when the random variable takes values lesser than 1 by 4. Now, here also by definition, the probability is defined as integration minus infinity to 1 by 4 fx dx. 1 by 4 is an element lying within this range. Okay, from 0 to 4, in this interval 1 by 4 is there. Okay, now I am breaking this particular interval into two halves again. One particular half is minus infinity to 0, and another half is 0 to 1 by 4. Now when x is lying between minus infinity to 0, you already know that it is undefined. So we are substituting 0 over here, so it vanishes. And when x lies between 0 to 1 by 4, since fx has value 1 by 4 root x for entire range, so for the sub range the functional value will remain same, because it is fixed. The functional value is fixed throughout the range. So we substituted the value of the function over here. Okay, you cannot substitute the value of the function instantly over here, because if we substitute fx equal to 1 by 4 root x in this particular step, that means you are sure that the functional value from minus infinity to 1 by 4 is that, but it is not true. So first you break it into two halves and then you substitute the value of the function. Now this becomes 0, and again you integrate and put the limits, and ultimately the answer, the probability will come out as 1 by 4. And if you think this as an area, it will be 1 by 4 units. Probability of x greater than 1. Now probability of a complement is 1 minus PA. So probability of x greater than 1 will be 1 minus probability of x less than or equal to 1. Equality sign was not included in this particular place, so it has been included here. So this by definition, it means integration from minus infinity to 1 fx dx. Again, you cannot substitute 1 by 4 root x instantly over here. So you have to break it into two halves once again. So I have broken it, one from minus infinity to 0 and another from 0 to 1. From minus infinity to 0, the functional value is 0 once again. You know it because fx is undefined. And from 0 to 1, since 1 is a value, sorry for the interruption. Just a minute. Now, sorry for the interruption. Now, since 1 is a value of x which lies within this range, from 0 to 4. Therefore, I have substituted the value of the function over here. I can substitute it. And therefore, we get 1 minus 1 by 4, 0 to 1, 1 by root x dx. You integrate once again, put the limits of the variable, and the probability will come out as half. So that is how we calculate the probabilities in case of continuous random variable. Next comes the definition, which is also very important and whose counterpart in discrete case has already been discussed. So what is the definition? First of all, let me define what distribution function is in terms of continuous random variables case. The distribution function is defined as fx, probability of x less than or equal to small x. This is nothing new to you. You have done 2 problems with respect to this particular formula. But only difference is, in the discrete case, here we wrote summation t less than or equal to x pt. Now I am going to write it, I'm going to represent it in terms of integration, and I'm going to integrate the function ft dt from minus infinity to x. And that is called the distribution function capital Fx, okay, when capital X is the discrete continuous random variable. Theorem says, now try to recall the theorem which we did in the discrete case also, that if the distribution function is given, how to calculate the probability mass function. Here also, they have said that there are, if suppose there are 2 functions, fx and capital Fx, small fx and capital Fx. Small fx is the probability density function and capital Fx is the distribution function. And suppose probability that capital X lies between a and b is defined in this way. You know it very well. It comes from the formula of definite integral. What does it mean? It means that if you integrate fx, we get capital Fx. If we integrate small fx, we get capital Fx. And if we substitute the limit, we get fv minus fa from the definite integrals definition. If it is so, then the probability density function fx is of the form ddx of capital Fx whenever the derivative exists. So these are the 2 definitions which are very important. I am going to show you an example on the basis of this definition. Let me skip this particular theorem for the time being from today's class. I am going to show you next a problem with respect to this particular definition. I am going to find out the distribution function corresponding to a given probability density function. So my problem is, show that the given function is a probability density function. Find the distribution function of the random variable. Sorry for the interruption once again. This problem is there since yesterday. Okay, so just I'm extremely sorry for this. Hope you can see my screen. Anyways, I'm going to show that a given probability function is there, and I'm going to prove that whether this function is indeed probability density function or not. And also I'm going to find out the distribution function corresponding. Anyways, just a minute. Okay, so I'm going to show you the problem first. This is my probability function. This is my probability density function. It is fx. It is represented by fx. It is not a probability density function, remember. It is just a probability function. They are saying that it is a probability function. I'm going to prove that it is a density function. So my fx is this. When x lies between 0 and 1, fx value is x. When x lies between 1 and 2, the probability function's value is 2 minus x. And it is 0 when it is when x lies between when x is less than 0 or when x is greater than 2. Here I can consider the negative values of x, because under square root sign is not there, square root symbol is not there. So here you can say that if x takes negative real numbers, the probabilities are 0. Okay, in the previous case it was not possible for us to say. So this is my probability function. Now I am going to claim that it is indeed a probability density function. because until and unless I claim it, you cannot say that a given probability function is probability density function. For probability density function, the function must satisfy this criteria that integration minus infinity to infinity ft dt, this integration must be equal to 1. Total probability must be equal to 1. So if you can show that the total probability is indeed 1, then only you can say that this given probability function is a probability density function. Now I am going to break this range into 4 halves. First half is minus infinity to 0, where the value of the function is 0. The last half is 2 to infinity, where the value of the function is 0. And the in between two halves are 0 to 1 and 1 to 2. From 0 to 1, when x is taking values from 0 to 1, the function has, the fx has value x. So I'm putting here ft. In place of ft, I'm putting t. I'm writing integration 0 to 1 t dt. And when x lies between 1 to 2, then we are getting the function's value as 2 minus x. So in place of ft, I'm writing 2 minus t dt. I'm integrating the function from 1 to 2. And if I do so, then if I integrate, the result is coming out as 1. So I am proving that the total probability corresponding to this probability function is equal to 1, and then only I can claim that this given probability function is a probability density function. Suppose I am giving you a chart, and suppose I am considering the discrete case, and I'm giving you a chart, a distribution where values of x and probabilities of x are given. Now, if I ask that, if I claim that it is a probability mass function, then you shouldn't believe me until unless you check that whether the total probability sums to 1 or not. If the total probability doesn't sum to 1, either in discrete or continuous case, then it implies that some values are missing. Data is not complete. The chart is not complete, and you cannot claim that the probability is a probability mass function or a probability density function. Only if this criteria is satisfied, then only we can say that it is a probability density function. Now let us calculate the distribution function for the given case. Now by definition, fx is defined as this. Fx is equal to probability of that capital X less than or equal to small x. We are going to integrate ft dt from minus infinity to x. Now here is a very important part is there, which I must mention. Try to look at it carefully, how I broke the interval into halves. I didn't break it like that. Minus infinity to 0, 0 to 1, 1 to 2, and 2 to infinity. Not like that. Rather, I am writing minus infinity to 0, 0 to 1, and 1 to x. Because if you break it like this, then you already know when x takes the value 2, then the probability is 0. So it will not affect something into the distribution function. And since it is a distribution function, the result must come out in terms of x. Okay, so therefore you have to be careful enough while breaking the interval, the range. And here small x is a number which lies between 1 and 2. Just keep that in mind. Otherwise, you cannot substitute that. Now we are substituting all the values over here. Here in this range, ft is 0. In this range, ft is t. And in this range, ft is 2 minus t. Integrate, I'm integrating the entire thing and putting the limits, and I'm getting the function as this. The fx is coming out as this, 2x minus x squared by 2 minus half. And that is how we calculate our function. Now, this is how to represent my density function, my distribution function in this particular case. Now, since distribution function is related to probability, that particular expression must be greater than or equal to 0. So I have written that for fx to be a distribution function, we must have 2x minus x squared by 2 minus half must be non-negative. And if you hello,
please allow Zoom access function for the best meeting screen Zoom may ask.
Hello.
Hello, sir.
Hello, can you hear me? Can you hear me, students?
Yes, sir.
Okay.
Yes,
So
sir.
okay, so if the integration, if my fx to be a distribution function, this particular expression must be non-negative. And if you calculate the limit, if you if you simplify this particular inequality, you will get that x is lying between 0.58 to 3.4. Now, after getting all this, I am representing my distribution function in the following form. I am saying that when x is less than 0.58, my fx is 0. When x lies between 0.58 to 3.42, my fx is of this form. And when x is greater than 3.42, my fx is 1. So this is how we calculate the distribution function if the probability density function is given. Now I am going to discuss one special case of a continuous random variable, which is actually known as uniform random variable. Now, uniform random variables are of two types. Uniform random variable can be discrete. Uniform random variable can be continuous. Okay, let me give you an example of a uniform random variable which is discrete. For example, if I say that I am going to toss a coin which is unbiased, and you already know that if the coin is unbiased, then in that case there is an equal probability for getting head and tail. That in that case, probability of head is half and probability of tail is also half. So the probabilities are uniform in nature, but the outcomes are discrete. One outcome is H and another outcome is T. So that is a case of discrete random variable, which is uniform. Likewise, if I toss a dice, which is unbiased, all the 6 spaces have equal probability of being selected, that is 1 by 6. And if you tabulate and if you write the values of x, the values of x will be 1 to up to 6, each having the probability 1 by 6. That is also a case where we can say that the discrete variable is uniform in nature. Here I am going to talk about a variable which is of continuous nature and uniform. Okay, look at this graph. Look at this graph. The graph has got the following shape. It's also sometimes called the rectangular graph. And it is saying that the function is defined only within this range from a to b. I am going to find the height of this particular density curve and the corresponding probability that x takes the value a plus b by 2. How to do it? Now, since it is a rectangle and the function is only defined in this particular range, and we know that a rectangle's area is given by the formula length into breadth. So we have to use this particular property to calculate the height of the rectangle. If we calculate the height of the rectangle, the height of the density function or the value of the probability density function will come out. Now the base of the rectangle has got length b minus a. And suppose the height of the rectangle is capital H, because we do not know what is the height of the rectangle. So we are assuming that it is capital H. Then by the property of the rectangle's area, we can write that length into breadth must be equal to 1, because since it is a probability function, total area must be equal to 1 if we integrate the function from a to b. So here I have written this equation that if we integrate the function fx from a to b, the area under the curve will be equals to 1. Okay, because the function is defined in this particular range. For other values of x, the function is not at all defined. Okay, so actually if we take the integration from minus infinity to plus infinity, then the total area is 1. But suppose I'm writing it here as minus infinity to plus infinity fx dx, then you are going to break the entire range into 3 halves. One is from minus infinity to a to b, and b to infinity. And you already know that from minus infinity to a, the function is not defined by the condition given in the question. From b to infinity, the function is not defined by the condition given in the question. It is only defined from a to b. So therefore, the total area from this, with respect to this range, will be equals to 1. And we are substituting, and total area, it's a rectangle, so the area will be b minus a into h. So this integration is nothing but equivalent to b minus a into h. And therefore, from there, I'm calculating h to be 1 by b minus a. So this probability function has the form 1 by b minus a. So what have I written? See, I have written over here that if capital X be a continuous random variable of the above type, and if its probability density function is defined like this, that when X lies between a to b, it has got the value b minus a, 1 by b minus a, and elsewhere it is 0, then such a probability function is called uniform probability function. Such a variable, random variable, is known as uniform random variable of continuous nature. Now, if I'm supposed to find the probability that X takes the value which lesser than a plus b by 2, that means you are going to integrate fx from minus infinity to a plus b by 2. Again, I'm dividing it into two halves. One from minus infinity to 0, another is from, minus infinity to a, and another is from a to a plus b by 2. In this range, the function has no value, so it is 0 over here. And a plus b by 2 is a term of x which lies between a and b. So in this particular range, from a to a plus b by 2, the function has got the value 1 by b minus. So I have substituted over here and I have integrated, and ultimately the probability has come out to be half. And it is indeed true, because since total probability from a to b is 1, so since a plus b by 2 is the midpoint, so in this particular range, the total probability must be equal to half, 50% probability. So such a random variable is called a random variable which is of continuous nature and uniform. So this is the expression for uniform random variable. Here I have given you a problem. Let me discuss the problem very quickly first of all. Okay, before that let me calculate if this is the functional form, what will be the expectation of the random variable and what will be the variance of the random variable if capital X is the continuous random variable of uniform nature. Now you already know that expectations value is formula is given by minus infinity to infinity integration x fx dx. So here also I'm doing the same thing, breaking it into three halves and substituting the value of fx for the range of x from a to b, and I'm calculating it, and I'm getting the expectations result to be a plus b by 2. And similarly for Vx, we need the formula ex square minus ex whole square. Ex has already been calculated. I need to find ex square, which has got the formula integration minus infinity to infinity x square fx dx. Integrate this and you will get this expression, b square plus ab plus a square by 3. You substitute and you subtract b square a plus b whole square by 2 from that, you will get the formula as b minus a whole square by 12. So these are the two important results for uniform random variable. So I have noted this down over here as a theorem. The theorem says if capital X is a uniform random variable of continuous type, and here X lies between a to b, the domain lies between a to b, ab is a subinterval of the real line, then the mean of the variable is termed as a plus b by 2, and variance of the variable is b minus a whole square by 12. Okay, and this formula you have to keep in mind. I'm going to use this particular formula in the next example. In the example, it has been mentioned that capital X is a uniform random variable defined in this range AB, and mean of the uniform random variable is 1 and variance of the uniform random variable is 4 by 3. I am going to find the probability of X less than 0. This can only be found if you know the value of A and B. So my first job is to find what is the range, what is the lower limit and what is the upper limit. For doing that, I am using this particular formula, which I have noted here. By the formula, we know that the mean of the uniform random variable is a plus b by 2. My given condition, it is 1, so I'm equating this to a plus b by 2 is equal to 1. And by the formula, the variance of the uniform random variable is b minus a whole square by 12. And by the condition, it is 4 by 3. So I'm equating these two. And after solving this equation, I'm getting the values of a and b to be -1 and 3. A is equal to -1, b equals to 3. Remember, while solving, since there is a quadratic equation, other possibilities will arise. You are going to reject those possibilities with proper logic. One of the logic is that remember that A must be less than B. And another logic that you are dealing with the probability density function. So do not consider any such value which gives you the probability as negative. So by applying those conditions, I'm getting the value of A to be -1 and value of B to be +3. And since the value of the probability is 1 by B minus A, okay, the value of the probability function is 1 by B minus A. I have got the upper limit as 3 and the lower limit as -1. I'm putting these two over here. So my fx is coming out as 1 by B minus A. That is 3 minus -1. That is 1 by 4. When x lies between -1 and 3. So my fx is 1 by 4 when x lies in the sub-interval -1, 3. And elsewhere it is 0. So we got the probability function for the given problem. And the remaining portion of the problem, I have kept it for you. It's a homework for you. For the time being, today you don't have to, before the examination, you don't have to calculate this, but you do calculate, find out the probability that x takes the value less than or equal, less than 0. Use the function and integrate from -infinity to 0. Okay, integrate, you have got the function now, so you are going to integrate the function from -infinity to 0 and see what value comes. This is a homework for you. So this much for today, students. I am going to end my today's class. Now the time is also running out. If after it gets disconnected, if you have any